Hello students. In today's class, we are going to actually look at an experiment in which a thermodynamically relevant quantity is being measured. So, the topic of today's lecture is experimental determination of the heat of neutralization of a strong acid by a strong base. And I am going to show you some actual experimental procedure by which this enthalpy of neutralization is being determined. So, let us go ahead and have a look. Now, the reaction that I am going to focus on is the neutralization of an aqueous solution of HCl, which is a strong acid, by an aqueous solution of sodium hydroxide, which is a strong base. I am going to perform this experiment at room temperature, and there will be an enthalpy change as a result of this reaction. So, that is the enthalpy that we are going to call as the heat of neutralization. And in today's lecture, I am going to find out how to use calorimetry to determine the heat of neutralization of HCl solution by sodium hydroxide solution. Since we are talking about the neutralization of a strong acid with a strong base, therefore, I am essentially talking about the reaction of 1 mole of H plus ion in the aqueous medium with 1 mole of hydroxide ion in the aqueous medium, producing 1 mole of water. So, this is the common reaction between any strong acid and any strong base, where a complete neutralization is being achieved. And in the reaction that I have with me today, that is HCl and sodium hydroxide, this is a well known exothermic reaction. So, I understand that if I add sodium hydroxide solution to HCl solution, there will be heat evolved, and I am going to find out how much heat has evolved as a result of complete neutralization of the given acid solution. So, here delta H neutralization would therefore be defined as minus Q divided by NW. Now, here Q is the amount of heat released due to the neutralization reaction, and since the heat is being released by my system where this neutralization reaction is taking place, I have added a negative value sign over here just to make sure that I am adhering to the sign convention that I have introduced to you in this course. So, it is negative Q, which means that the heat is being lost by my system comprised of the mixture of HCl and NaOH solutions. Now, what is NW? NW is the number of water molecules generated in my experiment. So, as you see, then Q will have the units of joules or kilojoules as the unit may be, and this would be moles. Therefore, you will get delta H neutralization as a negative number in the units of joules per mole. Okay. And here you understand that delta H neutralization with a negative sign is necessary because I have an exothermic reaction. Now, moving ahead, here is a typical experimental setup that you will find when you walk in any physical chemistry laboratory where an experiment like this is being conducted. So, let me show you the different parts of the experimental setup. You first see that there is a box like structure, and this is nothing but a calorimeter. Okay. I will come back to the calorimeter and what is there inside it, but as I will try to focus your attention to a small copper wire which is sticking out from the calorimeter, and this is a starter. And in this experiment, what we are going to do is we are going to use a starter that is using electrical energy for the starting action. Therefore, I would require a switch to power on the starter and a regulator which controls the speed of the starter. And as you see, attached to the calorimeter, there is another panel which gives you a digital display of the temperature of the two compartments that you see here. In the calorimeter, as shown by these two small windows, there are two compartments which are separate from each other. And this digital thermometer, this is connected to both the compartments, and this display shows the temperature of the left hand side compartment, while this display shows the temperature of the right hand side compartment. And I would also like to bring to your attention that I have a set of thermometers, the normal thermometers to perform the experiment. And as I have already said that I am going to use a starter which uses electrical energy for its action, I would need some power supply. So, here I have a power supply for both the action of the starter and the digital display. So, this is your experimental setup, and you are going to carry out the calorimetry of the chemical reaction, neutralization of HCl by NaOH. Let us next have a look at the list of chemicals required for my experiment. I am going to use 100 milliliter of 1 normal hydrochloric acid solution. I will react this hydrochloric acid solution with 101 milliliter of 1 normal sodium hydroxide solution. And if needed, you can check if your reaction is complete and you have a complete neutralization of the given hydrochloric acid solution. In that case, you can use an acid base indicator such as phenolphthalein, which will be colorless in the acidic medium, but it will assume a pink color if the mixture of acid and alkali is slightly alkaline. Now, here you must realize that I am using a slight excess of the sodium hydroxide solution. The reason of doing this is I want to ensure that there is a complete neutralization of the given hydrochloric acid solution. Okay. So, with this, let us now go ahead and revisit the chemical reaction that we are going to study. So, if I take 100 milliliter of 1 normal HCl solution, how many moles of H plus I am starting with? I am starting with 0.1 mole of HCl. So, I have here 0.1 mole of H plus ion, and that will be reacting with how many moles of sodium hydroxide? I have in the medium 0.101 mole of sodium hydroxide. Of these, I require 0.1 mole of sodium hydroxide for the complete neutralization reaction. If that happens, then I will have 0.001 mole of sodium hydroxide excess in the medium, and this neutralization reaction will now produce 0.1 mole of water. Therefore, I understand that the number of water molecules produced NW actually is 0.1 mole. Okay. Now, going ahead, I know that delta H neutralization is minus Q by NW. When I know that NW is 0.1 mole, I understand that in order to find out delta H neutralization, I need to find out Q. So, let us next see how we can go ahead and measure Q, the amount of heat evolved using the calorimeter. So, that is the next step, but before doing that, let us have a look at what is there inside the calorimeter. As I said, I have two compartments of the calorimeter, and in each of the compartment, this is a schematic representation of all that I have within the compartment. First of all, you have a polished copper vessel. This is the outer copper vessel, inside which there is a polished copper inner vessel, and this inner vessel is put in here and held in position by a fiber ring. And then an insulating cover is attached, and there is an insulation all around the outer layer of the entire calorimeter. Now, in this entire setup, what I have here is through a small hole, there is a copper stirrer attached. So, when you lower this entire setup inside this bigger compartment, what you can do is, if I am adding some solution to the inner vessel, I can stir that solution with the copper stirrer. Now, look at the top insulation cover. I have here a hole for inserting the thermometer. So, the basic idea is, before the reaction starts, I should be able to measure the temperature of the solution contained within the inner vessel, and then once I have started the reaction, I should also be able to measure the change in temperature by noting down the new temperature that that results from the completion of the neutralization reaction. Now, with all these set up in mind, then the question is, how do I find Q? If you would remember that if I am trying to find out the Q applicable for heating of a single substance, then Q is mass of the substance multiplied by the specific heat at constant pressure multiplied by the change in temperature due to heating. But here, do I have a single substance? The answer is no. I have several components within the compartment where my acid base neutralization reaction will take place. So, I understand that the heat released by the chemical reaction will heat up different things. First, it will heat up the solution contained within the inner vessel. It will heat up the calorimeter and its different parts. It will heat up the stirrer, and it will heat up the thermometer which is inserted in the solution. And therefore, I understand that in order to find out Q, I must note down not only the change in temperature as a result of the chemical reaction releasing heat, but I should also take into account the combined contribution of all the components which are present in the calorimeter setup that I have shown here. Therefore, I must say that how do I estimate this summation highlighted over here in green? I must be having summation over I Mi Cpi running over all the necessary components which can get heated up by the released heat as a result of the chemical reaction. So, the first term obviously will be mass of the solution multiplied by specific heat of the solution. I will then add to it the contribution coming from a product of mass of the calorimeter multiplied by the specific heat of the calorimeter. Then I will add to it a third term coming from the mass of the stirrer multiplied by the specific heat of the stirrer, and then I will have the last term added to it, which is mass of the thermometer into the specific heat of the thermometer. So, when you go and do this experiment in the laboratory, all these quantities, that is the 4 masses, you can independently measure. And you can either find out the CP solution from literature, or since I have used copper as the material for the calorimeter and stirrer, I know what the CP values are going to be, and we can use the CP of the thermometer from the available data that is provided with the scientific thermometer. Okay. So, as you understand that all these data would be known when you are performing this experiment. So, then the question is, how do I do this experiment? So, let me show you quickly how this experiment is done. So, before you start your experiment, you start off by having, this is the one normal HCl solution, this is the one normal HCl solution, this is the one normal sodium hydroxide solution, and then I have taken some measuring cylinders. In these measuring cylinders, I have measured out 100 ml of each of the acid and alkali solution, and here I have a smaller measuring cylinder where I have kept an additional 1 milliliter of the alkali solution. So, let us start the experiment. So, let us now have a look at how the actual experiment is done. So, first what we will do is, we will take the sodium hydroxide solution and then take 100 ml in the bigger measuring cylinder, and then in the left hand side compartment I will pour the entire 100 milliliter of sodium hydroxide solution, which is one normal, and I will also add the additional 1 milliliter that I have here. Now, I have added the sodium hydroxide solution and have closed the lid, and then I insert this thermometer to the lid of the sodium hydroxide solution. Now, I am adding to the right hand compartment the hydrochloric acid solution. So, 100 ml of one normal HCl solution, and again I attach the another thermometer, so that I can go ahead and measure the temperature of both the solutions under the given experimental condition. And as you will see that from the digital display, I find that the two solutions are actually differing a little bit in temperature, and that is probably because they were not being maintained at equal temperature. But if you wait for some time, what you will find is that their average temperature will become more or less the same, and that is what is expected, because there is no interaction between the two solutions and they are in thermal equilibrium with the surrounding temperature. Now, I remove the lids and add the sodium hydroxide solution to the HCl solution, and then I immediately have to cover the calorimeter, so that I minimize the heat loss that might occur during the evolution of heat as a result of mixing. Okay. Now, what I will do is, I will reattach the thermometer in the acid alkali mixture and switch on the stirrer and stir it very well. Okay. Why do I need to stir? Because I really want to complete the reaction, and in such a way that I start seeing the temperature changing over here because of the heat which is evolved as a result of the neutralization reaction. So, we started from a temperature of about 21.3 degrees centigrade, and as you can see, by continuous stirring, the heat evolution is being completed, and the temperature over here is it is turning out to be going on increasing, and as you see that the temperature increases up to about 27.4 or 27.2 degrees centigrade. So, after it goes up to 27.4 degrees centigrade, it has started decreasing. So, at the end of the experiment, what happens is you have come down to something about 27.1 degrees centigrade, which is what is expected. So, what is it that you will do at the end of this experiment? You are going to report the experimental data, and obviously you will prepare some tables in which, in a very systematic manner, you are going to present the temperature values that you have recorded, both from the thermometer as well as from the digital display. Okay? And then what you can do is, the first thing that you note down over here is you must note down the room temperature, because whatever you are doing is pertinent to the room temperature, and then you start plotting your experimental value. To start with, you will be plotting the average temperature of the acid and alkali solution that you had before mixing, when you had the acid solution and the alkali solution in two different compartments. So, let us say that these are the points that you have recorded before mixing, and then after mixing you have these points. Okay? So, what you have to do is you have to draw the best fit straight line through these segments. As you see that there are two different segments over here, and we are going to draw two best fit straight lines over here. And then I would also note down during the experiment, using a stopwatch, the time I started mixing the two solutions and the time I ended mixing the two solutions. So, the beginning and the end time, if you take an average between the duration, you will get what I denote as the average mixing time. So, at this time I will draw a vertical line, and this will tell me what the behavior of the system was at the mean time of mixing. And as you see here, I have extrapolated both the lines before mixing and after mixing in such a way that I can see the points of intersection between these two lines with my vertical line, which I show here at t equal to T mix, so that I understand that this is giving me an accurate representation T1 of the temperature right before mixing, and T2 is the temperature right after mixing. And then what I say is I will calculate delta T as T2 minus T1. Now, the question you might ask at this point is, why did I do it? I obviously had the data points from my experimental observation, then why did I have to draw a graph? As you understand that the way you have done the experiment, you required a finite time to add the solution, and during this addition, what happened was the lid of the calorimeter was open. So, this plays a crucial role in our decision as to how we are going to interpret our experimental data. Let us go back and look at what is happening here. I see that before mixing, the average temperature of the acid and alkali solution kept in the two different compartments are more or less the same, and that is the reason why it is a nearly horizontal line that I have got here. Now, when you took out the alkali solution, opened the lid of the calorimeter containing the acid solution and started pouring, immediately heat started evolving. And then the system, which is now an open system during mixing without that lid, there will be immediately heat loss, irreversible heat loss from inside the calorimeter to outside. Was this present before the mixing? The answer is no. Before mixing, both the acid and the alkali solution were present at an average value of say about 21.4 degrees centigrade, and as you see that the room temperature, it was also 21.4 degrees centigrade. In the absence of any temperature gradient, there was no measurable heat flow between the system, that is within the calorimeter, the two solutions within the calorimeter, and their surrounding. Now, after you mixed, because the reaction is very fast, immediately heat starts evolving. Therefore, from inside the calorimeter, the temperature has jumped to by about 5 to 6 degrees centigrade. So, you are going on mixing, the lid is still open, and that is a scenario where the solution inside the calorimeter is about 5 to 6 degrees hotter than the surrounding air outside the calorimeter. Therefore, a heat flow will immediately set in. Okay? So, after you have finished mixing, you have closed the lid. Now, this kind of fast irreversible heat flow will be arrested. Why is that so? That is because the material with which the calorimeter is being prepared, has been prepared, is a poor conductor of heat. Now, what will happen? With the calorimeter now being a closed system, the heat will slowly seep out from inside the calorimeter to outside. Why should it still seep out? That is because, as you can see, right after mixing, still the temperature of the solution inside the calorimeter is about 5 degrees higher than the temperature of the surrounding, which is the initial temperature as you have seen here. So, still there is a temperature gradient, still I would expect heat flow from inside the calorimeter to outside, but now the heat flow is going to be very slow because of the way we have fabricated the calorimeter, making it a very poor conductor of heat. Therefore, if I wait long enough, I will see that the temperature is slowly going down of the solution. This is because, as I said, a slow heat loss through the walls of the calorimeter, which is an imperfectly insulated system. So, now what I do is I assume that here the heat loss is so slow that the temperature of the system of my acid alkali mixture, which has been neutralized, will be linearly decreasing with time. And that is the reason why I have connected these points with a straight line and extrapolated it backwards. Now, what is this particular point? This particular point tells me what would have been the temperature of the solution or my experimental setup inside the calorimeter if I did not have the irreversible heat loss during the mixing procedure. Therefore, I would say that this is a much more accurate estimate of the temperature that has resulted from the release of the heat as a result of neutralization of HCl by sodium hydroxide. So, once you do that, once you know delta T, then you can find out Q by multiplying the summation which you know for your setup into delta T, and then what is delta H neutralization? You have produced Q amount of heat, the reaction has released Q amount of heat with the production of 0.1 mole of water. So, you will go ahead and say that delta H neutralization would be a ratio of Q and NW with a negative sign, and in general if you have performed an accurate enough experiment at a room temperature of about 20 to 22 degrees centigrade, you will find that delta H neutralization will turn out to be about minus 56.3 kilojoules per mole, or if you are using a suitable unit in other units, it is minus 13.4 kilocalorie per mole. So, this concludes our discussion on how to measure the heat of neutralization of an acid solution by an alkali solution. As you see that it is very easy to write down H plus plus OH minus giving me H2O, but when you actually carry out the experiment, it is much more thought provoking to have a correct interpretation of the experimental data that you have obtained in your experiment. And do not forget the negative sign, because after all you have used and studied an exothermic reaction. Thank you.